I actually want to do one more example with the integral test. Um, so determine if the series converges or diverges. So you could try the zero limit. Alright, so if I take the limit of that, well, this is k squared over k cubed, right? So since the smaller power is up top and the bottom power is on the bottom, this is definitely going to go to 0. So by zero limit, this means zero limit test fails. So let's try. So can I integrate this? Well, yeah, I can. If I get, if you look at this as an integral, you could do u substitution for k cubed plus 2, right? Then that'll cancel out with the k squared. So let's try the integral test. All right, so first condition. Is it positive terms? So, that's pretty easy. That's pretty easy to see, right? If you plug in 1, 2, into infinity, you're going to see that this is a positive term series. Yes, it is. Is it continuous? Is it continuous? So if I let this, if I replace this with f of x, make that x squared over x cubed plus 2, right? Is it continuous? Well, yeah, it is. It is continuous because, if you look at this, the only time this is going to be undefined is when k cubed plus 2, when this is equal to 0, right? So this will be discontinuous when or in other words, if you solve that for x, you're going to get x cubed equals negative 2, right? Which would mean x equals the cube root of negative 2. Which, if you use your calculator, is negative 1.25. So this is a negative number, right? So, I don't care about it because I'm only interested on the values that are greater than 1. So is this going to be discontinuous for these values? Yes, it is. Okay. Is it decreasing? So how do you find out if this is decreasing? Take the derivative. So how do you take the derivative of this? Well, you use the quotient rule. Low d high minus high d low over low squared. So when you go through that, you're going to have low d high minus high d low all over low squared. So when you go through that computation, if I do a little simplification here, right? So if I distribute the 2x and multiply this out and do combined like terms, the numerator is going to reduce to 4x minus x to the fourth all over x cubed plus 2 quantity squared. And if I do a little bit more reducing here, just factor out the x, I'm going to get x times 4 minus x cubed all over the denominator. Right? So that's what my derivative looks like. Now, is that going to be, is this less than 0 for x greater than equal to 1? Is it? Well, if I look at this, so that's my derivative, right? Well, when x is greater than 1, the x is obviously going to be positive. Now, what about this quantity? So I have 1 cubed. So I have 4 minus something cubed. Well, that's positive. Okay. But for, you know, if I plug in 2 there, right? So if I plug in 2, well, 2 cubed is 8. Right? So 2 cubed is 8, so 4 minus 8, that's going to be negative. So initially it looks like it's going to be positive, but then as I keep going here, this is eventually going to become negative. So this will become negative at some point. And then this whole thing is squared, so that's obviously always going to be positive. Something squared is always positive. So I have a positive times a negative divided by a positive, which is going to be negative. So that means this will be less than 0. So is this going to be, yes it is. So hence, the function is decreasing. So since it's decreasing, so is it decreasing? Yes it is. It's decreasing, it's continuous, and it's positive. So now I can apply the integral test. So, you know, if you're not convinced by this, you know, if I plugged this function into my calculator, all right, let's graph the derivative here and just look at how it looks, all right? So I have x times 4 minus x cubed divided by x cubed plus 2 squared. All right, so if you look at the structure of this graph, I'm only interested on values that are greater than 1, right? So let me adjust this that the lowest value I have is 1. And let's look at the graph now. I might have to adjust the window again. You know what? It might have to, hold on, let me go on the other way. Negative 0.001 to well, trying to get a good idea of what these values should be between. Alright, so here's what I want to get at here. If I graph this, right, what's going to happen here is that when I plug in some values into my first derivative, I don't want to spend too much time on this example, but I'm trying to find a good values for y so that'll show a nice curve, but I'm having a little difficulty with that. Let me guess negative 0.1 to 0.1. Alright, well, as you can see here, it looks like the graph is starting to increase initially, which you might think is a problem, right? Because it's supposed to decrease for the integral test. But actually, when you plug in, so if I look at the values here, right, if I start at 0, right, actually, so when you plug in 1, right, it's a positive term. But when I plug in 2, it actually becomes a negative term. And then when I keep going, right, the terms, as you keep looking at it, they actually start to decrease, right? Initially, it starts off positive, but then it slowly starts becoming negative. So this function initially looks like it's... So what's going on here is that if I graphed the function, right, it's starting off positive, right? It starts off doing this, but then it eventually starts decreasing like that. So it looks like it's starting off positive, but then it starts to decrease. So, at x equals 1, for example, that could be right here, but then eventually it starts decreasing. That could be x equals 1, but then eventually it starts to decrease. So what's going on here is, just to make a note, the function looks like it's increasing, but after x equals 2, the terms eventually decrease. So therefore, f of x is actually decreasing. It looks initially like the integral test won't apply here, but it does. It takes a while for you to see it. It starts off increasing, but since it eventually does decrease, it's okay. It's good enough. So the integral test applies here. So now take the integral from 1 to infinity of x squared over x cubed plus 2 dx. So how do we integrate this? Well, this is an improper integral. So this time I'm actually going to, I'm going to do that first. So let's rewrite this as the limit as b approaches infinity from 1 to b, x squared over x cubed plus 2 dx. Now how do we integrate this? Use substitution, right? U equals x cubed plus 2. du equals 3x squared dx. And dx equals du over 3x squared. So the limit as b approaches infinity of the integral x squared over u, and dx becomes du over 3x squared. So the x squareds cancel, which is beautiful, and we end up getting the limit as b approaches infinity of, now I have a 3 here, right? Well, I have a 1/3 here, so I'm going to write that outside the integral of du over u. Now, if I notice how I'm not putting 1 and b here yet, because I want to integrate this first. I mean, I could integrate this with respect to u if I wanted to and change the bounds of integration. So I could do that here. Like when x is 1, what is u? I plug 1 in here, I get 1 cubed plus 2. That's going to be 3, right? And then if I plug b in here, right, that'll be b cubed plus 2. If you want to do that. Or you could just integrate it in terms of x. Or, I mean, evaluate the bounds in terms of x is what I mean. But either way is fine. Okay, so when you integrate this, you're going to get the ln of u from 3 to b cubed plus 2. Or you could just write it as ln, what was u originally? X cubed plus 2. Right? And you could do that from 1 to b. Either one of these is just fine. You know, if you replace the bounds in terms of u instead of x, just using the u sub, you could do that here, or you could just evaluate the bounds in terms of x after you replace u when you integrate it. That's up to you. So if I do this now, okay. So if I do this, I'm going to use this one. Plug in the bounds, so I'm going to have the natural log of b cubed plus 2 minus the natural log of 3. All right. So if I take the limit here, what's this going to go to? Well, the limit of b, so b is going to infinity, so infinity cubed is still infinity. Infinity plus 2 is infinity. So I'm going to have the natural log of infinity. What does that go to? Well, ln, you know, ln of infinity, so you should know that ln of x, right? Natural log of x. Let me make some normal bounds here. So ln of x, it goes to infinity, but very slowly. So this is going to go to infinity very slowly. So that's what that goes to. It goes to infinity very slowly. So I have infinity minus ln of 3, which is still infinity. Okay, so that means the integral does what? The integral diverges. So what does that mean about the original series? Since the integral diverged, so I say therefore the series from k equals 1 to infinity of k squared over k cubed plus 2 also diverges by, remember, cite the test, the integral test. That's it. Don't forget to cite the test that you're using when you're doing this. So, you know, the only difference here is that the function didn't look like it was decreasing right off the bat, but eventually it does. Like if you plug in the first derivative, if you plug in x equals 1 into your function, it's going to look weird, but eventually it's going to decrease. It'll initially have positive terms, but then as you go on, it's going to start going down, which eventually decreases is the same thing as decreasing in this context. So we're actually okay. We're fine. So an additional example using the integral test. So now I'm actually going to go on to the next section. So that's it for that problem.